Now what we're going to do today is take our knowledge of factorials, fundamental counting principle, permutations and combinations, and apply them to our basic principles of probability. The first thing we need to understand is related to probability what an experiment is. And an experiment is a situation that just has several possible outcomes. So then that creates a sample space, which is that set or list of all possible outcomes. So for example, if we're rolling a number cube, the sample space would be 1, 2, 3, 4, 5, 6, because it's not that there are 6 possible outcomes, that is the size of the sample space. We're taking a look at exactly what the sample space is. What could we get? Now on this one, spinning this spinner, we have the options of red, blue, green, or orange. And so from there, once we have our sample space, we can then come up with our probability, which is going to be that number between 0 and 1, or 0 and 100%, that indicates the likelihood that an event will occur. So, for example, we could take a look at it on a spectrum here, like we have here, that goes from 0, which is impossible, all the way to 50%, which is as likely as not, or equally likely, to 100%, which means it is certain. And when we look at the probability of an event, we want the total number of possible outcomes in the denominator, and our number of favorable outcomes, or what we want to happen, to be in that numerator. Now, if we're looking at the complement of an event, complement is going to be the sum of all probabilities in the sample space being 1. Complement is the probability of it not happening. So 1 minus the probability of it actually happening. And then once we get that far, probability can break into 2 pieces. As you guys already know, there's theoretical and experimental. I define theoretical as what should happen. If we had a perfect world, what would happen? So for example, if we flip a coin, probability of getting heads should be 0.5 or 1/2, because we have 2 sides, one of those sides is heads. Experimental probability, on the other hand, is what actually does happen. It's the likelihood of an event based upon what has already occurred. So the number of times the event occurs over the total number of trials. One of the biggest things to make sure you're careful about when you're calculating experimental probability is if we say that Bobby makes 50 out of 75 free throws, and we say what's the probability that he will make the next free throw, it is not 51 out of 76. We cannot predict the future, so we go based upon what we already have. If a baseball player has a 250 batting average, it's not going to change when we make predictions based upon his next at-bat. We use that to judge how likely he is to get a hit. So, taking a look at some common experiments in their sample spaces, if we toss a coin, options for sample space are head or tail. 2 coins, heads, heads, tails, tails, heads, tails, tails, heads. Rolling a die or a number cube, 1, 2, 3, 4, 5, 6. Picking a card would be one of 52 different cards in that playing deck. Or if we roll 2 dice, I have a picture here of the sample space that you could get, or all possible outcomes. There are 36 of them. So the next thing I want to do is learn how to calculate theoretical probability. So when we look here, we have a bag of marbles. Inside we have 1 red, 1 blue, and 1 green. So we need to find the probability of getting red. Well, I count that there are 3 marbles in the bag, 1 of which is red, which means that the probability of drawing red is 1 out of 3. Now the probability of not getting a green would be 1 minus 1/3, because it's a 1/3 probability of getting green. So 1 minus 1/3 is a 2/3 probability of not picking a green. Finally, we have the probability of a purple. And as you can see, there are no purple marbles in the bag, which means my probability is 0 because it is impossible. Looking at example B, we want to roll a 6-sided number cube once. We need to then find the following probabilities. I want you to go ahead and try this one, and then once you've entered your answers, go ahead and hit play, and you can figure out if you did it correctly. So now let's roll this 6-sided number cube, which we know our sample space is going to be 1, 2, 3, 4, 5, and 6. So probability of rolling an even number. I know that my evens are 2, 4, and 6, which is going to be 3 out of 6, which simplifies to 1/2. Please simplify your fractions if you can, because it's a lot easier to wrap your brain around a smaller fraction than it is one with bigger numbers. Now, when we look number less than 6, all of these are less than 6. So therefore, that is 5 out of 6, and that cannot be simplified. So now, let's take a look at rolling two 6-sided number cubes. We're going to scroll back up to look at the picture as we go. We want to look at a sum of 7. We don't want anything less, anything more, we want 7. And when I look here, I see that we can have 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. So when I count that up, 1, 2, 3, 4, 5, 6. So we have a probability of 6 out of 36, which simplifies to 1/6. Probability for a sum of 3. When I look here, I see that if I take 1 and 2 and 1 are the only ways I can get 3. That's 2 of them out of 36. Both of those can be divided by 2 to get 1 out of 18. A sum of not 3. Well, we already have the sum of 3, which means I need to take 1 minus 1/18, which means my probability of getting a sum that is not 3 is 17/18. A sum of less than 10. When I look here, I see that my borderline is right here of getting 10 or higher. These are 10 or higher, which I have 1, 2, 3, 4, 5, 6 of them. So that means that 36 minus 6 is 30. So I have 30 out of 36, which can simplify to 5/6. A sum of 1. As we know, when you roll two number cubes, the smallest number you can get is 2, which means that my probability is 0. To get a sum of less than 13, I see that the biggest number that I can get is 12, which means that everything is less than 13. So that means my probability is 1 or 100%.